Okay, thank you very much. So what I will do is I will start with an introduction. So I apologize to those of you who know already everything I'm going to say, but I think it's a rather wide and diverse audience here, so it may be useful to get a generic introduction about dynamic mean field theory, and the predictions that we get from it. So yeah, this is more or less the plan of the talk. I am going to talk about aging, weak long-term memory, and time representation invariance, and then Jorge will do the second part and talk a little bit more about new challenges, new ideas, and things to be done in the future. But before doing that, let me just tell you that, I'm replacing Marc Mézard as editor-in-chief of J-StatMech. So this is just, to tell you that it's a very nice journal, and that the themes covered by this journal are the ones of the school. So, welcome to submit papers there. Give me your ideas, impressions, and suggestions if you want during the rest of the week. I'm going to be here until the end of the week. Okay, so it's an introductory talk. The plan is I'm going to give you some examples of many body systems in interaction and why they undergo slow dynamics, interesting behavior in time. I will tell you about the example of domain growth, coarsening, which is the simplest one to understand, and dynamic scaling. And then the necessity to introduce or to look at correlation functions and linear responses. So Irene talked already about linear responses yesterday in cases in which it's not so obvious to identify a growing length. So they behave a little bit like the generalization of other parameters for these dynamical problems. And then I will tell you, some ideas about dynamic mean field theory and what we can get out of it, and leave the stage to Jorge after a little break for the new stuff. Okay, so let me just mention some examples. We know about, spin glasses, or not necessarily spin glasses, I mean just systems of spins in interaction, like something here. These are the part of the problems we are interested in. We also have particles in interactions, like colloidal suspensions, for instance, where you have potential energies that depend on the distance between the particles. And we can have more recent interest into problems where there are forces that don't derive from potentials. And this is an example of bacteria suspensions, active matter, and also Irene talked about this yesterday. So on the physical side, we have Newton's action-reaction principle. So interactions should be symmetric. So this is, for example, what's expressed here and also here. Interactions between the two elements, they don't depend on, it's a potential. We can define a potential like this. While in the biological realm, for example, or ecological realm, or other econophysics and these kind of things, you don't necessarily have forces that derive from potentials, and you can have these non-reciprocal interactions that came back to life very recently, and attracted the attention of many people these days. So some examples. The simplest example of collective non-trivial dynamics is the case of coarsening and critical dynamics. So this example is just pick a two-dimensional leasing model, for instance. You initialize it at a completely random initial configuration, with as many spins pointing up as spins pointing down, red and white, let's say, and let them evolve in contact with a thermal bath, with Monte Carlo or Langevin, or the dynamics that you like, stochastic dynamics that you like, at the either the critical temperature of the problem or below the critical temperature. And in both cases, what you see is that there are patches of red and white that grow, right? So here they're bigger than there, here they're bigger than there. The geometry of these objects is different at the critical point or below the critical point, by this idea that there is some length that is growing here and there in time is present in both cases. So there is some growth of order in this case that goes on in time. And for these problems, what happens is that this growth is such that if you wanted to cover the full system with one of the two colors, for example, here in the low temperature phase, you will need times that diverge with the system size. So in practice, for sufficiently large systems, you will never reach the equilibrium of being magnetized in plus or minus magnetization below the critical point, or reaching the correlation length of the equilibrium situation at the critical point, which diverges at the critical point. So in both cases, you would need times that diverge with system size to reach equilibrium. And if your system is sufficiently large, you will not reach it. Okay? But the mechanism that is trying to reach this equilibrium situation is clear in both cases. Is the growth of critical structures here, is the growth of domains of the same color in the other case. We understand it, we visualize it, and we can even describe it analytically, first phenomenologically if you wish, and next analytically with simple models. On the context of these active problems, for example, one of the cases in which you have injection of energy into the sample at the microscopic level, exactly as Irene was saying yesterday, you can have a similar situation depending on the parameters of your problem. So this is just an example of a simulation in one of the standard models for active matter in 2 dimensions. It doesn't matter so much the definition of the problem. The fact is that for certain values of the parameters, you see that you start from an homogeneous situation where the particles are, the density of the system is homogeneous everywhere on the sample, the same. And then as time goes on, what happens is that you have this separation into dense and dilute regions. The colors don't pay attention at them. When it's some strong color, you have a dense cluster, and then what you have in between those dense clusters is dilute. So you have a separation between dense and dilute regions, and this can also be characterized through a growing length that I'm just plotting here to give you an idea. These are the different parameters, and you have this growing length that you can use to describe the phase separation process that takes place in this problem. So even in this strictly out of equilibrium, some of these strictly out of equilibrium problems where you have the system kept out of equilibrium by this injection of energy, you can have something that you understand through the observation that there is a growing length. The growing length depends on time and depends on the parameters. So here phi is the packing fraction and P is the activity. So in these problems, we understand what's going on. Then it can be difficult or not, to try to characterize them analytically, giving all the details, obtaining this growing length, and so on and so forth. But, the mechanisms and what's going on, we understand. So there is a growing length, and we can use this growing length to apply dynamic scaling ideas and describe correlation functions in space-time and some of the properties that also Irene was describing yesterday about the behavior of these systems. One difference to be stressed here is that in the case of domain growth, for a finite size system, eventually the system will reach equilibrium, the normal one, described by the Gibbs-Boltzmann distribution. While in the active case, since there is this injection of energy that is continuously being made on the system will reach some non-equilibrium steady state. Okay, so the distribution of configurations will not be Gibbs-Boltzmann, will be something else, but still it will be some stationary situation for sufficiently long times. But again, if the system size is big enough, you will never reach it. Okay, but what about glassy systems that are of interest to many of you as well? We don't understand whether there is a growing length like the one that I mentioned before. At least visually, we cannot see it. Maybe there is, maybe there is not. We don't know. So, we cannot just simply look at configurations and extract this growing length from some smart analysis. So then, we go to use other kinds of observables, so define observables that can tell you something about different phases. So either you are, like in the paramagnetic phase, in the ferromagnetic case, for the case of the domain growth problem, or liquid glass in the case of particles in interaction. So what can we use to characterize those different phases? And well, these objects you have already seen, I think, in different lectures. Something that we like to use is self-correlation. For example, in the language of the spins, but you can use a different language and do density-density correlations or whatever the observable that is relevant to the problem that you have. But you correlate at different times those observables locally, for example, here, so it's spin-spin. And you sum over all of them, you do a global measurement like this over the whole sample. And here the angular brackets represent average over thermal history, so if you wish different experiments in the problem. And these these square brackets, sorry, are if you have quench randomness in a calculation, the average of the quench randomness. So this is quite natural and typical correlation function. Next, there is the linear response function that Irene was mentioning yesterday. So imagine that you perturb your system weekly at a given time, say TW, for example, and you look at the instantaneous response of the sample, how this observable changes due to the application of the perturbation at a later time, t. So this R is the instantaneous response, so you just kick it once and look later. This chi is the integrated one, so you kick it continuously. If this is time and this is the perturbation, let's call it H. So you start perturbing at TW, you keep the perturbation on, and you measure at time t. And this is the chi over there. So these objects sort of extend the notion of an order parameter for an out of equilibrium problem and tell us a lot about how they behave and to which kind of class the models and the systems belong, as I will tell you a little bit later. So in equilibrium, if the system were to reach equilibrium, these two objects should be a function of time difference only. This is a consequence of the Boltzmann equilibrium distribution. And also, they should be related by the fluctuation dissipation theorem that tells you how one depends on the other one. And I will come back to this later on. Out of equilibrium, there is no obvious relation between these two, and one can try to see how they compare one to the other and learn about the dynamics of the system in that way as well. So how did these problems, these these correlations and linear response behave? The left is a sketch. The right one is simulations on Lennard-Jones mixture, so one of these standard models for glassy problems. So what you see for the correlation is that there is this aging phenomenon when you go below some temperature or above some density. And what you see is that these correlations don't depend on differences between the times, but they depend on the two times in a non-trivial way. So you have these decays that depend on T weighting. This is short, this is long. And the decay is slower the longer the T weighting. So different curves are for different T weightings. And so the T weighting is like here, T is like there. This is a correlation without perturbation. So there is H equals to 0. You just simply compare the configurations, and you see that the decay of these correlations is T-weight independent. So it's non-stationary, it's out of equilibrium explicitly. Now, something else that you can observe from the analysis of these curves, which is clearly expressed here because it's a sketch, and I can do it as perfect as I want. So what you observe is that there is a decay of the correlation towards a plateau first, something that you would see here in these numerics, and then decay from the plateau towards 0 in a slower and slower manner as T weighting increases. And ideally, this separation is through a very flat and perfect constant value of the correlation, which I'm calling Edwards-Anderson parameter. Okay, so in both cases, the plots, as I say, here is in function of T minus TW, and this is the correlation that you're measuring. So if you want to put this observation of separation of timescales into equations, what you do is you say, okay, there are two contributions. The correlation is the sum of a term which is stationary. The first approach to the equilibrium, you see all the curves go together. So here, there is only a function of T minus TW that you have. And then there is a second contribution, which is what I'm calling C-aging of T and TW, which has the T weighting explicit dependence in it. Now, it turns out that in most of the cases that we simulate or we analyze analytically with different approximations and so on, we can always write these two terms as a function of the ratio between two functions that depend on the two times separately. Okay? So let's focus on this one. So the second part, you can scale if you assume that this function here is the function, external function, scaling function of the ratio between these two r's. I don't know what's r. That's all. In this case, I don't know what's r. I cannot see it visually. But it turns out that I can scale it in this way, both here and also here, by just the simplest trivial proposal that the r that I have to use is an exponential. So then when you divide one by the other, you have a function of t minus tw. So in both those pieces, both contributions can be written in the scaling form that you would also have for coarsening systems, only that in coarsening systems you know what's r. You can see it. Here, in general, you don't know it, but it happens that you can do it this way. Actually, there is a way to prove that you have to have 4 different time scales a scaling of this form. It just follows from monotonicity of correlation functions and some positivity of them, and some very general assumptions. But okay, I will not go through that. Okay, so what do I conclude from here? That there is aging in these glassy problems. Older systems relax more slowly than younger ones. There is a separation of time scales with these 2 scales, and we can always scale on each scale the correlations through this kind of a scaling form. Now, what happens with the linear responses? So I'm plotting chi, because it's order 1, let's say. Well, I shouldn't say it's order 1. It's something which is easier to measure numerically, because you are integrating something which is very small over a long period of time. So in the end, you have something that doesn't fluctuate that much. If you were to measure the instantaneous response, it fluctuates a lot. Numerically, it's difficult to control. But this integrated version, this kind of susceptibility, is easier to see how it behaves numerically, experimentally, and so on. So the counterpart of the correlations decaying in 2 regimes, when applied to the chi, well, it's sort of turned around, right? So you have an approach to a constant here, and then you have a departure from the constant that depends on t weighting in the same order, in the sense that older systems go towards the asymptotic value of chi in a slower manner than younger ones. But you also have this separation of timescales into rapid and slow, and into stationary and non-stationary. Now, this is what happens in glassy models, models simulated, analytically solved, and so on. In coarsening problems, like the domain growth problem, is different. So in coarsening problems, what you see is that the waiting time dependence of these curves, these are simulations from this group in Salerno, is going down with t weighting. So the asymptotic value, the asymptotic form, of this integrated response will be an approach to a plateau and just remaining in the plateau. And this we see in all the examples that we know of. We don't have a generic proof that this should be the case, but it happens in all the cases that have been studied. So there is this difference that one can see from the behavior of the linear response between proper glassy problems, let's say, and coarsening problems that is otherwise not seen in the correlation function. So in a sense, this is telling us more about the behavior of the system. It's more rich, it's richer than the self-correlation functions. Okay? I'm not going to talk about the recent results by Silvio and collaborators on the problems that show strong memory of initial conditions that fall a little bit away, not completely into the picture that I'm going to show you, but you can discuss with them, with Silvio, if you are interested later. Okay, so there is this idea that the memory can distinguish between coarsening systems and glassy systems. In glassy systems, the part of the linear response, integrated linear response, also scales as the ratio between 2 functions are, while in coarsening problems you have a prefactor that depends on the total time. That is a power law, typically, in all the problems we know of, that makes it just, saturate to this constant in the long time limit. So this, I should have added here aging. I forgot about that. So this is the part of the aging contribution that it's represented in this slide. Sorry for that. There is a typo there. Okay. But as I said, there is no obvious interpretation of this R in the aging glassy systems. Now, how to model these things? How to try to capture these things with analytical calculations applied to some models? So, well, for this audience, I shouldn't have included this slide, but okay, it came from a different presentation, so I kept it. The idea is that we use mean field models. So we use models of agents or spins in interaction all-to-all, and this allows us to go ahead in the calculations very far away. And the simplest example of this kind is, of course, the Curie-Weiss model for ferromagnetism, but this is just too simple. Then what we do is we generalize this case to problems which have more complicated interactions and that are able to characterize to give us information about glassiness. Of course, the fully connectedness that we use for the physical problems is an approximation, but for other problems that you all know of is the real problem that you want to solve. So I shouldn't necessarily justify the fact that we use fully connected models here. Okay, so what about the potential energies that we use? The kind of classical model that we use is this p-spin spherical model. So we have interactions between p spins, only that they are not easing. They're not plus or minus ones. They are spherically constrained. Okay, let me jump over that. They have random interactions between them, so couplings drawn from some probability distribution, and we give Langevin dynamics. So we give Langevin dynamics of this kind. This term enforces the spherical constraint. This is the variation of this potential with respect to psi, and then you have a noise. Okay, so if you use p equals 2, so if you use interactions between pairs of spins here, spherical ones, it turns out that this model is like the standard model for coarsening. We recover all the phenomenology of the coarsening problems that I mentioned until now. While if you use p larger or equal than 3, you are more in the class of the random first order transition used to describe fragile glasses that I think you have already heard of as well. So the beauty or the nice feature of these problems is that in the large n limit, so for n going to infinity, one can derive for these problems exact equations that control the evolution of my two order parameters, so the correlation function and the linear response function. This is the instantaneous one, but okay, can be transformed into the integral one as well. And these equations have the form of what they are called Schwinger-Dyson equations. They are causal integral differential equations that look well complicated, but you can solve them numerically, for example, put them in a computer and solve them, and build the form of the C and the R in the course of time. You can also solve them in the long time limit, taken after n going to infinity, because the equations hold only for n going to infinity, with some tricks. Okay, so you can get information about the full time evolution of these two objects, and you can also get analytical information about the long time limit of those objects as well. Okay, so the identity of the model is embedded in this self-energy and this vertex here, that for the p-spin case, okay, take these power forms that are given there, but for other models with other kinds of potentials, you will have other forms for these kernels that will change a little bit the specific structure of the equations, but not the global. The global will always be of this kind for these spherical models. Now, these equations are very general, and they don't only, these kind of equations, I mean, they don't only apply to this model that I introduced at the beginning. So, for example, if you are interested in using, instead of white baths, so noises which have memory, color baths, so with some memory kernel in it, well, what you have to do is change this friction term into that one, and also change another term in the equation, but I'm not writing it, but it's very simple. I mean, you can cover with these kind of equations also color bath. You can cover non-reciprocal interactions by changing the relation between the sigma and the d. If you look at the structure of the sigma and the d in the other equation, well, you can see that sigma is like the derivative of d with respect to c, this term here, times the response. Okay? So if you change the relation between the sigma and the d, then you are mimicking in a simple way, these non-reciprocal interactions. You can also select special initial conditions in the equations that I showed you. I was thinking about the completely disordered initial condition, and the evolution was controlled by the temperature, which is here, so by this, at which temperature I evolve is over there, but these don't have information about the initial conditions. They suppose random initial conditions. While if you want to include information about special initial conditions, you can also do it. It's just the addition of some terms in these equations that takes into account that. You can also look at, for example, Newtonian dynamics. This is interesting in the case of, in the context of what people are doing, for example, for integrable problems, quantum dynamics, and so on. People are interested in looking at the evolution of problems which are not connected to a bath. So this you can also do in this context. You simply have to change this friction term, so it shouldn't be there, but you add a second time derivative of Newtonian dynamics, and then you have that case included also in this structure. And you can also do quantum, by changing, in the quantum you have to change the bath kernels, the self-energy and the energy form, but it's also of that kind. So there are many physical examples or problems that people look at that can be captured through these kind of Schwinger-Dyson equations and their solutions. Now, some kind of surprising predictions from the solution of these equations, that the nice thing about it is that you have the equations, you solve them, and then you see what happens. You don't have to make an assumption about what's going to happen. You solve them numerically, you see what happens, and then you try to understand analytically why you got that and try to interpret the result. So one of the outcomes of the solution of those equations that came as a surprise is the fact that although out of equilibrium you don't have to have any relation between the correlation and the linear response, the integrated one I'm plotting here because, as I said, it's better behaved, it turns out that from the solution of those equations there is a modification of what is the fluctuation dissipation theorem of equilibrium, which is very simple. So let me explain it in this way. So Irene showed a picture like this yesterday. I am repeating it here. So what is plotted here is the integrated linear response against the correlation function, where you fix t weighting and you let t increase. So I have, these two objects. I fix this one very long, so that this separation of timescales that I claiming exists here is well developed. There is a nice plateau here, and there is a nice plateau there, very long. And then I let t evolve. So t will evolve from t weighting to infinity, say. So I start plotting chi against c in this parametric way where I increase t. So I start from correlation 1, let's say that correlation is normalized, to 1 at equal times, and then correlation decays and the chi increases. So I'm moving upwards. In equilibrium, the relation between the two is just a straight line of slope minus 1 over the temperature of the bath. So it's just a very trivial relation, linear relation between the two with this slope over there. This is the prediction of thermal equilibrium à la Boltzmann. What happens in these problems is that you have a first part which follows this straight line and a second part which follows another straight line. In the P models with P larger than 2, the glassy ones, and just 1P. Okay, so it's in a class of problems. Now, the breaking point is located at exactly QA for the correlation function and at exactly chi EA, the plateaus. So until the plateau, it goes like in equilibrium. After the plateau, it goes with a different slope. It goes with a different temperature. So if you want to call this an effective temperature, well, you're 1 over the effective temperature, you're tempted to do it, right? Because you have a straight line here and a straight line there. It appears in the same way, it has the same units, Okay, so this is the solution from the model. You have it, you see it, this is what happens. Now then, you can try to give an interpretation to this second slope as an effective temperature. In these problems with the slow dynamics a la Glassy Systems, this can be done. Irene said yesterday, you don't have to say that this is an effective temperature. It depends on the problem. In these problems, this object, this parameter that appears here in the violation of FDT, admits an interpretation as an effective temperature, and this is nice because if you have something that you think it's a temperature, then you can use thermodynamic ideas, you can give sense to many observations that otherwise would be a little bit mysterious. So, you have a framework in which you can include what you find. Okay, I will not talk more about this, but I just want to mention that in certain cases with slow dynamics, this violation of FDT admits the interpretation of an effective temperature. Relations to landscapes, you heard a lot about landscapes for sure from Valentina during the week. These dynamics that I'm describing with this FDT violation and this aging and so on, for these models corresponds to the relaxation from some random initial condition to a region in these rugged landscapes that these problems have, to a region that here is not represented. So you should imagine that there is a region here that is flat. So you have a rugged landscape, and you relax, okay, something like this, and imagine that there is a region that is flat. And that for some reason, for those pure models, the basing of attraction of the relaxation of a random initial condition is to this region which is flat. And this can be shown analytically again from the solution of these problems and from the analysis of the rugged landscapes for this problem. And moreover, if you want to look at how big this flat region is and what is its entropy, and configurational entropy of this, and try to relate it to a microcanonical temperature, you will get the same value of the microcanonical temperature from here that you get from the FDT violations. So this is another, if you wish, indication that you are really talking about a temperature in that case, and this calculation that I'm telling you about, relating microcanonical entropy, relating configurational entropy to microcanonical temperature is something that Rémy Monasson did, and also Silvia with Giorgio had results over there in the 90s, I don't know, 90 something. I don't remember exactly. I didn't put it in the slide. Okay, this I said already. Now, let me tell you a little bit about time reparametrization invariance. I'm sure that Jorge will say more about this later on. So, say more? Yes? No? Okay. So, let me tell you about this. So, I told about this separation of time scales. And this is something that, again, it's the equations that are telling us about. It's the solution of the equations that are pointing us into this direction of talking about this. So I have, the fast I forget. Let's forget about the fast because it's boring. The interesting part is the slow, which is below this plateau. So the aging part, as I told you, they can be scaled using a scaling variable that is these ratios between two R's, which I don't know what they are, but okay, there are two R's, let's say. And this scaling variable is order 1. Now, if the aging part is scaled like this, and I take the derivative with respect to time of this aging part, I will see that it affects this R dot over R TW. Sorry. Well, okay, I do the derivative. And I will see that the derivative of this will be proportional to R dot over R. Times a function that is also a function of this ratio, which is order 1, and I'm not writing here. So, in the limit of long times, say that, for example, R of t is some growing function like power, for example, to make the simplest possible case. Well, this goes to 0. If you take a log, it will also go to 0, and so on and so forth. So for all reasonable functions R of t which are growing in time, you will get that the derivative over the value of the function itself goes to 0 as time goes on. So this means that this is much smaller than that. And indeed, this is what allows us to solve those equations analytically in the long time limits, where we can assume that this derivative is much smaller than the function itself. And in this sketch here, this is assumed. I mean, this is simple to see. This is a double log scale, and the derivative of this part here is smaller than the function itself, and the value of the correlation itself. Now, if you look at those equations, complicated Schwinger-Dyson equations, and you drop the derivative, and you work a little bit with all the integrals that were on the right-hand side, you realize that the equations acquire an invariance under t going to any function h of t. Okay, so let me show it in more detail here. So say that I pick the equation for the linear response to make it simple. So say that I focus on time such that the Lagrange multiplier that enforces spherical constraint converges. The two, both correlation and response, are in the aging regime, in this regime of scaling. I drop the time derivative of the response with respect to the right-hand side. And OK, I'm left with this equation after massaging a little bit the integral on the right-hand side. Everything depends on the agent contribution to the correlation and the linear response. And now it's just a question of two lines calculation to show that if I change time into a function of time, and by doing that, I keep the form of the correlation function, and I change the form of the linear response function in this way, this equation remains unchanged. So it remains, keeps the same form, which is sketched, it's written down in the last line over here. It's the same equation as before, only that instead of written in terms of t, it's written in terms of h of t. So this is this time reparametrization invariance that arises in this long time limit in these equations when I can drop the time derivative, say that this converges to a constant, and looking at what's remaining in the equation. So let's see, what did I say here? So this means that in the context of the solving the equations, what we can do solving the equations, once we realize that by this dropping of the time derivative we have simplified the equations, is that we can obtain analytically the relation between chi and c. So this slope over here we can obtain. We can obtain the value of the Edwards-Anderson parameter. We can obtain the function, the scaling functions that are outside. But we cannot fix R. So because there is this time reparametrization invariance, whatever function of time I put here will solve those equations, approximated equations that I had. So I cannot fix the clock, let's say, the velocity with which the dynamics takes place in time. That I cannot fix, but I can fix relations between correlations of this kind and many other ones if I wanted to look at higher order correlation functions or things like this. So time cannot, the clock cannot be fixed in this approximation. Okay, this is a long time approximation in which I drop the time derivatives. If I were to keep the time derivatives, I could do it. And if I do it, numerically by solving the equations step by step in time, it is fixed, this scaling variable on this R of t over there by the actual solution, complete solution of the equations. But in the approximation, it is not. So which are the conditions for this time reparametrization invariance to arise? We think, but again, this is not something that is proven in all the possible details, that weak long-term memory, in the sense that the aging part of the integrated response should be order 1, is necessary. Why do I say that? Because if we try to do the same arguments for example, the P equals 2 spherical model, or the ON model for ferromagnetism, or all the coarsening problems, this doesn't work, because the linear response has this dropping term that is scaling with time in front of it, and this breaks this time reparametrization invariance. I cannot just simply drop the time derivatives, basically, in these Schwinger-Dyson equations. I have to keep them, compare to what happens on the other side of the equations, work much more, and realize that the equations are not invariant under this transformation. They are only invariant under time rescalings. But OK, this is something that is observed in several cases, but there is no strict proof of this. So this is, if you wish, is something that to me is something open. Then there is open problems related to these mixed p-spin models, where you put two p-spin terms together in the potential, and there have been works by Silvio, Federico, Francesco, and Folena in the past, where they have seen no weak long-term memory, strong memory of the initial conditions. They fall a little bit away from this picture that we had, but okay, this is something again that is to be understood completely. And then there is this nice model by Pier Francesco, these canyon-like models. I was talking to him this morning. I think that it would also be interesting to see what happens in that problem from the context of looking at the linear response and looking at what happens with this time reparametrization invariance if you want to look at their solution from the Schwinger-Dyson equation. So these are some open problems which I think are interesting. Now, last thing to say is in the past, many years ago, but now Jeppe Dire is picking up into these ideas that Claudio Chamon had, and he developed with me and other people years ago, is to try to use this reparameterization invariance to say something about the fluctuations. So what we're doing in those papers is to say, okay, I have this scaling for the global correlation function. This I observed, it's sure, let's say. Now imagine that instead of looking at the full system, I start looking at pieces of the system, and I try to look at how the correlations for different pieces compare to each other. So the fluctuations of the correlations on different pieces. And the claim is that since we have this time regularization invariance arising in the long time limits, it should be very easy to make the internal functions in this scaling form fluctuate, while it shouldn't be so easy to make the scaling function fluctuate. This is like a more completely, how should I say it, constrained by the fact that I have to have the same effective temperature everywhere in the problem, because otherwise I would not have partial equilibrations and things like this. So the idea of the effective temperature behind the dynamics of these problems led us think that this should be easy to fluctuate, this shouldn't be easy to fluctuate. What does this mean? What it means is that imagine that you look at the correlation function in different regions of the space. So this is one, this is another one, that's another one. They could decay differently, right? Because there will be fluctuations. So they could decay differently, and this is a sketch of 3 different correlation decays. Now, if this is true, what should happen is that if you compare the correlation function and the linear response in each of these different regions, so correlation function and linear response for this region, so on and so on, what should happen is that this could be advanced or delayed in time, but they should respect this relation between the linear response and the correlation that dictates this effective temperature. So this point here, the correlation decays very quickly, so the correlation is lower, but the response should be higher, so as to be on this red line. And for this yellow one, the correlation decays slower, the response should be weaker, and it should be over there, and so on and so forth. Okay, so this is something that this was the claim, the guess or the proposal that is embedded in this expression here, and a similar one for the linear response function. And we checked it numerically in some, this is a list of numerical checks in some different problems. As I said, Jeppe is picking up these ideas and doing it experimentally, and I guess that Jorge will say something about this or not in his discussion. So let me mention that a little bit like what high energy people did more recently for the SYK model, where they also have this invariance and the time reparameterization. With Claudio, we wrote effective action for how these things should fluctuate based on some assumptions. Okay, this is something that we haven't really checked, and that this can be done also quantum mechanically. Also, Claudio did it with Malcolm Kennett, and I'm not going to discuss that. But okay, more recent, and this is Gimenti's poster that is over there. Fred van Disselen, Jorge, Ludo, and him looked at the idea of thinking about the fact that perhaps all these accelerated algorithms, like the swap algorithm of Camille and Ludovic, could be understood, the reason, or the way in which they work, as a reparameterization of time. The fact that you're looking at the picture with a faster camera, let's say, or you're making it run faster, I should say, better. So that this could be related to reparameterizations of time. So I'll let you discuss with them if you wish. So let me stop here. What did I say? So I told you some lessons from solving equations. So the equations, no doubt, they are exact for the models that we deal with. So we can solve them numerically and analytically up to a certain point, the analytical solution of them. But they told us things that we were not expected. So this is nice. And I told you some of the things about the FDTs, the effective temperatures, the time regularization invariance. Of course, each problem has its own peculiarities, and there is much more to say than what I said for each of them. Here, a list of similar problems like large D approach to glassiness, the ecological models that we heard a little bit about, neural nets, non-reciprocal interactions. Of course, I mean, there are many problems that have their own little details, but some of the things that I said apply to all, and they are quite generic, and I think it's a nice, like a global set of results that, well, should be right, should be correct. Okay, so thank you.